Let's look a little at the global carbon cycle in the context of the ocean uptake. So I'll show two figures from the European Union putting out these, especially led by Pierre Friedlingstein. It's showing the perturbation averaged over 2009 to 2018. So it's the representation of overall perturbation of the global carbon cycle caused by anthropogenic activities averaged over that period. And you can see there is volcanic, so we are looking at fossil fuel emissions, land uptake, ocean uptake, land use change emissions, and there are some budget imbalances and atmospheric increases and so on and so forth. So there is the fossil fuel emission about 10. So you can see there are uncertainties in each number. So these are in gigaton CO2 per year. So you can see the global reserves are shown, which we will ignore for now, and we will come back to the permafrost and soil pools and so on, and just focus on let's say this one here, ocean. So ocean has certain pools like the marine biota and the organic carbon, and then deeper ocean has much more massive pools like the dissolved inorganic carbon of 38,000 gigatons. So this is where I said if you do the residence time by dividing it by the flux of 2 gigaton per year or so, you get very long residence times, or 0.2 gigaton per year, for example. Okay, so the atmospheric CO2, because of this fossil fuel emissions increase, is at plus 4.9 gigaton carbon. Sorry, it's carbon, not CO2. And the total reservoir size is 860. Actually, it should be CO2, gigaton CO2. We always struggle with these units in our community. I don't know why. Okay, you can see that these are all in gigaton carbon, and then there is CO2 here. Random mixes, nonetheless. Just keep in mind that there are conversions involved. Let's just focus on the process. The process I want to focus on is that the ocean takes up 90 gigaton carbon for photosynthesis and exchange, and 90 gigaton is respired back. So the net uptake over this period is 2.5 gigaton carbon. Okay, so this is what we are trying to look at in this part. Later on we will look at the land part, which is here at land uptake of should be 3.2 gigaton carbon. So the main thing to remember here is then that we are perturbing the carbon cycle by putting in CO2 into the atmosphere, and the carbon cycle is acting to stabilize it by taking away the carbon into the land pool and the ocean pool and leaving the rest in the atmosphere that we can much more easily measure. Measuring it in soil and the ocean is of course much more difficult. Nonetheless, right now you can think of, despite the budget imbalance of plus 0.4 gigatons, the carbon cycle is a stabilizing or a stable system right now, since the Industrial Revolution. The numbers change a little. I wanted to include this just because this is the following year's report averaging over 2010 to 2019, as opposed to this one which averaged over 2009 to 2018. And just look at some of the numbers here. This one, this one, this one, for example. The atmospheric accumulation is at now plus 5.1 gigaton, and here it was 4.9. So we are accelerating the accumulation, and it's jumped to 860 as opposed to the same number here. So the reservoir size didn't change that much. The number here is almost the same. The land has gone from 3.2 to 3.4, so there is some increased uptake in the land just by adding another year. The main thing to remember is that we are always looking for a small difference between large numbers. 90 in, 90 out with 2.5 globally averaged difference that is attributed to ocean uptake, and here similarly 120 in, 120 out, and 3.4 is a tiny fraction of that, with land use change like deforestation, urbanization, agricultural land conversion, and so on, emitting carbon from land. So that's the net source. Okay, so this is a tough business in that sense of tracking, but people obviously track it all the time. As for the ocean, there is another group that systematically tries to track the invasion of anthropogenic CO2 into the ocean. This is a nice figure in a paper led by Nikki Gruber. There are other people who work with him, it's a group that works together all the time. And this is showing the delta anthropogenic carbon in micromole per kilogram, and you can see that it's going into each ocean. Calculating this is not so easy. You use tracers like tritium, which were released into the atmosphere, and then source was turned off because of Montreal Protocol and so on. And you can track its invasion into the ocean to track the age of the water masses, and then you have to separate the natural carbon which is in the ocean interacting with biology, circulation, and so on, and use nutrient ratios, metabolic carbon, etc. to derive the anthropogenic part. It's a very tough business, but this is done anyways with some uncertainty. So you can see the patterns that actually make sense, right? Here you are in the Atlantic, where there is deep water formation, so you can see the invasion going much deeper and into the southern part across the equator. These are, of course, the subtropical gyres where the surface waters converge and are downwelling. So you can see greater invasion in those subtropical gyres. In the Indian Ocean, you have a monsoonal circulation, so there is no gyre in the northern hemisphere, but there is one in the southern hemisphere, which shows that. And the Southern Ocean, of course, is a different beast because it has a channel configuration and it has a deep invasion of the anthropogenic CO2, as well as the heat from the global warming as well. Okay, so overall, to look at the uptake by the ocean, there is evidence that the if we look at the emissions, we looked at this figure before. So we are looking at fossil fuel sources which are well constrained, land use change which is remained flat here, somewhat well constrained, not completely well constrained. Ocean continues to increase its uptake as we are increasing CO2 in the atmosphere from emissions, so it's a negative feedback in terms of what the atmosphere sees and how the warming is amplified. So it's a stable carbon cycle in that sense. Atmosphere is still accumulating more, but not as much as if land and ocean didn't take up more and more. So you can see both land and ocean are taking up more and more. So in that sense, we are in a stable part of this carbon cycle. So the question is, will it continue to do so as we keep increasing the emissions and the warming keeps increasing in the atmosphere and ocean, glaciers start melting and so on. So there is the imbalances shown here. These differences are imbalances which we had shown in this figure here, for example. So keep that in mind. And the other thing is that there are also natural variabilities happening. For example, ocean was taking up about 1.9 gigaton carbon. This is CO2 again. Oh, sorry, this is petagram carbon per year. So you have to just get used to the units being flipped around. And it seemed to drop here from about 1995 or so to 2000, and then it has been taking up more and more. Obviously not here, but in these regions where there is uptake of human-produced CO2. Okay, and the Southern Ocean is a big part of that as well. Okay, so there are circulation changes, biology changes, wind changes, exchanges, flux changes, and so on. This part obviously is negative, so it continues to emit, and it has increased because the trade winds have strengthened over this same period. So overall, oceanic uptake of human produced CO2 has gone up, which is a good negative feedback as well. So we'll come back to the land uptake and future of carbon cycle together in the next podcast. But you get the idea that constraining these things is difficult, but we must continue to do that. But the message is fairly clear that in the present day, CO2 is basically trying to stabilize the system in response to the increasing fossil fuel emissions from human activities.